Hello, everyone. Welcome to today's class. And today we'll start to talk about unsupervised learning. And we will use two lectures to talk about it. And in the last lecture, we probably will talk about one example of unsupervised learning. Okay. All right, let's start from part one, clustering. So now we are here, okay, unsupervised learning. So first, let's review what's the difference between unsupervised learning and supervised learning. So in an unsupervised learning problem, there is no response variable. So we only have a bunch of feature variables, X variables. And the goal usually is to understand the relationship among them, among these observations. Try to figure out some patterns or clusters or some unknown features. Okay. So they are called unsupervised learning algorithms because there is no Y variable to supervise the learning process. So no Y variable to guide the process. So that's why it's called unsupervised learning. Now let's first take a look at clustering. So clustering is used to identify different groups of similar objects in a multivariate data set. Multivariate means there are many features in the data set. There are a lot of different types of clustering strategies, like partitioning methods, hierarchical clustering, density-based clustering, etc. But in our class, we will only focus on the first two methods, partitioning methods and hierarchical methods. So start with partitioning clustering. So this clustering method subdivides the dataset into a set of K groups, where K is the number of groups pre-specified by the analyst. So if we want to use partitioning clustering, we need to first decide how many clusters are needed. So probably we need to visualize the data and guess how many clusters there are in the observations. There are two main methods. The first one is called K-means clustering, and the second one is called K-Medoids clustering. And K-means was invented earlier in 1967, and K-Medoids was invented later in 1990s. They are kind of similar, we will see. Let's first take a look at K-means clustering. So each cluster is represented by the center or mean of the data points belonging to the cluster. So the problem is basically finding the cluster centers. And then given a new observation, you will allocate the new observation to that cluster based on where the center is. So the main goal is to figure out the centers of those clusters. And K-means algorithm measures distance between points with the Euclidean distance by default. Because all of these calculations depend on the distance. Right? So how to measure distance by default, the K-means method uses the Euclidean distance. For example, if we have two-dimensional data, the distance between 2 points is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, the straight line distance. This is a Euclidean distance. Right? And K-Medoids algorithm measures distance between points with a generalization of the Manhattan norm or L1 norm. So this is the default behavior of the K-Medoids clustering. However, the key difference between these two is not related to the metric that is used to calculate the distance. It depends on something else. Okay? But what is Manhattan norm or Manhattan distance? It is the straight line distance. So it is the sum of these two edges in the triangle. That's the sum of these two. X1 minus x2 plus y1 minus y2, absolute values. Okay? And the most common algorithm in the K-Medoids clustering method is partitioning around Medoids or the PAM method. And they have their strengths and disadvantages. So the K-means method is more sensitive to outliers just because of the metric, and also it relies on the mean of each feature variable. And K-Medoids is more resistant to outliers. Consequently, it is less sensitive to outliers because it relies on medians, the median of each feature. And also the metric is also more resistant to outliers. All right, let's take a look at K-means first. So this one is an algorithm-based approach to find K clusters in the data set. It uses a heuristic update strategy to make clusters as far as possible and each of the clusters as tight as possible. So at the same time, they want to make clusters as far as possible, the distance between any two clusters as far as possible, and at the same time, make each of the clusters as tight as possible. So namely, try to reduce the radius of each cluster, the area of each cluster. The smaller, the better. So it is not an exclusive method. Namely, it cannot consider all of the possible clustering ways to cluster these observations. It's because it is just the computation load is too heavy. For example, suppose we have 25 observations in the training data set, and we want to cluster them into 4 clusters. Okay, K equals 4. Then let's see how many possible ways to cluster these 25 observations. Okay. So let's use 4 cells to represent the 4 clusters. 1, 2, 3, 4. Okay. Then take the first observation. How many ways to assign the first observation? Consider X1. How many ways to cluster the first observation? It can be put in cluster 1, 2, or 3, or 4. So 4 ways to do so, right? And then the second observation, same thing. You also have 4 options to cluster X2. Totally 16 ways already, right? And consider all of the observations. Suppose we have n observations. Then you need to multiply for n times. So totally n of them. Then it will be equal to 4 to the these many ways. If n is 25, then it's equal to 1.259 times 10 to the 15. So this is a total number of ways to cluster 25 observations into 4 clusters. So you see, it's impossible to consider all of these possibilities. Instead, it will do it in a more like heuristic way or greedy way, and the algorithm will stop at some local optimum. And it must stop, otherwise it will take forever to finish the whole searching process, right? And the K-means algorithm actually uses this heuristic method. So let's see how it works. The algorithm iteration begins with an initial guess for the K cluster means. So basically, at the beginning, it will randomly choose K centers for the K clusters. It's purely random. And then for each observation, cluster it to the closest center, right? Cluster center. And then after that, after each observation is clustered, we will update the center, the cluster centers, namely recalculate the cluster centers, calculate the mean of each dimension. And then in the next iteration, we will, for each observation, cluster it to the closest mean again. So let's see one example. Suppose we have two-dimensional data. The scatter plot looks like this. And at the beginning, the algorithm will randomly pick three centers. One, two, three. Suppose we want to cluster the data into three groups. Okay. And these 3 points are just totally randomly chosen. Okay? And they are not belong to the data set. Remember that. Okay? So these are just 3 random points in the two-dimensional plane. Okay? And then for each observation, we calculate the distance. For example, let's consider this point. Let's consider this point. We calculate the distance between the point and each cluster. And since this point is closest to this, let me see. So calculate the distance between the point and each center. And since the point is closest to this one, this is chosen as the center for this point. So the point is clustered to this center. We do the same thing for all of the observations. And then the first iteration is done. So you see after the first iteration, these points are clustered to this center. We can call it A, B, and C. So all of these red points are clustered to center A, and all of these green points are clustered to center B, and then these blue points are clustered to center C. And then we update the centers, namely we recalculate the center for each cluster. So then you see cluster A, the center is here, and C is here, slightly changed, but B, the center of cluster B changed a lot, from here all the way to here. Right? So this is a updating process. And then assign observations to the centers again, right? The closest center again. Right? So the program will stop when it's not necessary to reassign observations anymore. Right? Well, let's see some terms. In math and physics, the centroid or geometric center of a plane is the arithmetic mean position of our observation in the figure. So for two-dimensional data, so they are basically x bar, x1 bar, and x2 bar. So for example, this is x1, this is x2. And the center is the mean of each dimension. It's called the centroid or geometric center. So this is another example with a different initial. So see in this case, the first two centers are clustered together, very close. And then the third one is here far away from them. Okay, then this is the initial assignment, and update the centers, and then assign observations again based on these updated centers. And this is yet another initial. So these are the first 3 centers, 1, 2, and 3. Initial assignment, update the centers, and then reassign. Let's see one example. We will use the faithful data set. So this data set contains the eruption times in minutes and the waiting times to the next eruption in minutes for the old faithful geyser in Yellowstone National Park. So it only has 272 observations and 2 columns. The first column is eruption time in minutes, maybe 3.6 minutes or 1.8 minutes, etc. And then the waiting time to the next eruption. So the waiting time is much longer, apparently, right? So so both of these two are feature variables. So we'll treat them as feature variables. So let's take a look at the data first. So from the scatter plot, we can tell that there probably are 2 clusters. Very obvious, right? So based on the density of the points, there should be at least 2 clusters, right? Corresponding to longer waiting time and longer eruption time and shorter waiting times and shorter eruption times. Okay. And then for very simple data sets, okay, like the faithful data set, it's easy to identify how many clusters are needed. Easy to tell by visualizing the data. However, for high dimensional data or for data sets that are more complex, it's very difficult. Sometimes it's very difficult to figure out how many clusters are needed. So there actually is a package which can help us to identify the optimal number of clusters that are needed. So the package is called Fractal Extra. If you want to play with it, yeah, please install it. Okay, you need to install it because so this part will be covered in your exam too. So you definitely need to install it first. And the function we use is this function. Just input the data set and then specify the method that we want to do clustering and calculate how many clusters are needed and specify the method. So here we use gapstat. There are many methods that can be used. For details, check this link. Check this link. So this is an essay about an article about this package. So we just chose this gap statistic. The larger the better. The larger the better usually. So this is a result. This it identifies it illustrates the best option using this dashed line. So apparently for our faithful data set, the optimal K is 2, which is consistent with our expectation. There should be 2 clusters. It seems that the K with the largest gap statistic should be chosen. But actually, the algorithm does not strictly follow that strategy. The strategy is that the optimal number of clusters is the smallest value of K such that the gap statistic is within 1 standard deviation of the gap at K plus 1. So namely, we try to find K such as gap K is greater than or equal to gap K plus 1 minus the standard error of the gap K plus 1. Okay. So see, for example, here, so this is gap 3, right? This point is gap 3 minus standard deviation of gap 3. Okay. So this point is greater than the lower limit, right? Lower 1 standard deviation limit, okay? Greater than the G2 is greater than G3 minus standard error of G3. Right? So, and this is the smallest K that it happens, right? If you observe the plot, you see this one won't work, right? K equals 1 doesn't work because it is not greater than this, okay? So that won't work. However, this point is also greater than G4 minus standard deviation of G4, right? However, this is not the smallest K that this inequality happens, this inequality is true. The smallest K is 2 when this inequality is true. Is satisfied. And so that's why the optimal K is 2. It's not 3 or any other of them. Okay. So basically, we follow the principle of parsimony. Try to build the simplest model such that the data can be explained or modeled well, like the simplest model. So the smaller the number of clusters, the simpler the model. So we choose the smallest K that this is true. Okay. All right, so this is how we find the optimal K. And then we know that the optimal K is 2. We can apply the K-means method. So R has this genetic function in base R, K-means. You just need to specify the data matrix and how many centers you need. And save the result here. And then this result is a list. Again, it has different components. The centers components contains the coordinates of the two centers. So the first center is at 4.22979 and 80 something. So the eruption time is 4 point something, and waiting time is 80 something. So it's corresponding to a center here for this cluster 1. And the other one is 2.1 and 54 something. So it's somewhere here, the other center. Okay. So this is one component of the output. And you can also take a look at the cluster labels. So this cluster component contains the labels. Since there are only 2 clusters, the algorithm assign 1 and 2 to the clusters. And this plot, and then we pull out we add the cluster information to the original data set and create this scatter plot. So basically, we map the cluster label to color. You see, it looks pretty nice. All right, so this is the first try. However, notice that the 2 variables have very different scales, right? If we take a look at this scatter plot, see waiting time is from about 40 to 100, but the eruption time are single digits, from 0 to 6 minutes. And because the K-means method highly relies on distance, it's very sensitive to distance. And the distance is very sensitive to the magnitudes of variables. It's better to scale the data before we apply the K-means algorithm. So that's why we first should scale the data. The generic R function scale can be used to scale the data. So it will minus the mean and divide it by the standard deviation. So x j minus x. So x bar divided by s. For each column, it will standardize the data. And then we apply the K-means function again using the scaled data on the scaled data. And then the centers will be different, coordinates will be different, and the plot looks slightly different too. So now, if we draw a border for the classroom result, so it's somehow like this. You have 2 ellipse areas instead of previously, the data is separated in this way somehow. Like you have two rectangle areas. All right. And an alternative way to do the scatter plot is to use this function, uh, favorite cluster function. Also, this function is building the package that we use to figure out the optimal number of k. Right? So, so this function is kind of more flexible. You can draw the borders. You can choose the shape. So, for example, I choose convex, and so then we see this kind of convex polygon drawn up around the two clusters. And also, you can choose the palette, and you can also it also just use the observation index to label each observation. So this is particularly useful to identify the observations in the border area, in this area, and identify the differences using different strategies. For example, this first data plot, actually, this first plot is about the result using unscaled data. You see, we use K-Mod1. So this one does the data is the raw data. It looks like this. If we use scale data, K-Mod2, so you see it looks like this. It's more like ellipse shapes. And notice that there is an argument called stand. So stand is a logical variable. If it is true, then in the plot, both x and y variables will be standardized. So you won't see the original values of the two variables. So, although the algorithm might have standardized data, however, the plot will show it. So you see this one. Although when we fit Mod2, we scale the data first. But if we choose stand equals false, we still can see the original values for x and y, although the method used to scale data. So this one is better than this one. You see the difference between 211. Original was cluster 2, but now it's in cluster 1. All right. So that is K-means method. Okay. And the second method is K-Medoids. K-means relies on means, right? The mean of each feature. And now K-Medoids. So what is a medoid? A medoid can be defined as the object of a cluster whose average the similarity to all objects in the cluster is minimal. So it is kind of like it's a point in the cluster. First of all, it is a point in the cluster. It's one observation in our cluster, and it is the sort of the median, right, of observation in the cluster, which has the smallest distance, average distance to all of the cluster in the cluster, all of the observation in the cluster. Right? So it is the most centrally located point in the cluster. Yeah. So medoids are similar in concept to means or centroids, but medoids are always restricted to be members of the data set. But in the K-means method, the centers or centroids are not in the data set. Okay? They are just some points in the plane. In contrast to the K-means algorithm, K-Medoids chooses data points as centers, and the most common realization of K-Medoids is the PAM algorithm, partitioning around medoids. Okay. Let's see how it works. So first, initialize. Okay, select K of the N data points as the medoids. Still, the initialization is random. Okay, so randomly pick 3 points as medoids first, right, from the data set. Right. Of course, we still need to decide how many clusters we need. So K should be pre-specified first. Right. And then associate each data point to the closest medoids. So still we need to measure the distance between each point and to each medoids. and then allocate or assign the observation to the closest Medoid. So this is the second step. And then the third step, for each Medoid M and for each non-Medoid data point O, swap M and O, and then associate each data point to the closest Medoid and recompute the cost or the sum of distances. So let me use a very simple example to show it and to let you better understand it. So consider a cluster with 4 points. Okay, so suppose this is the Medoid of this cluster. And these three observations are like O1, O2, and O3. And the Medoid is called M. I'll just call it M. So after the first assignment iteration is done, then swap for each Medoid and for each observation, each non-Medoid data point in the cluster, we swap them. So namely, we will make, for example, make this the new Medoid, okay? And then make this Medoid on observation, a regular observation, O pi. Okay? And then we calculate the distance between each observation in the cluster from the new Medoids. This is the new Medoids, and calculate the cost function. Basically, in this case, it's the sum of distances, summation of dj squared. So j is from 1 to, for example, n 1. Right? So that is the total number of observations in the day. So recalculate the sum of distances. Right? And if the total cost of the configuration increased in the previous step, undo the swap. Basically, we compare the new sum of square distances and the original sum of square distances when the Medoid was still this one. Okay, so compare them to. If the distance, sum of square distance decreases, we keep the swap. Otherwise, we undo the swap. Okay? So we do the same thing for all of the observations. Basically, try each observation in the cluster. Try to find a better Medoids in the cluster, basically. Okay, that is the whole process. And we'll do the same thing for other clusters. Yeah. So namely, so the main difference is the center now has to be a point in the cluster. And we do this swapping process again. Yeah. All right, now let's see how to apply the PAM function. The PAM function is in this package called cluster. Again, please install it, right, and play with the code. And feed the data set baseball. And there is an option called stand. So we don't have to scale the data by ourselves. So we can just let it be true, right? And the algorithm will standardize it. And then choose the metric. Usually we use the Manhattan metric for the K-Medoids method, but you don't have to, okay? And K equals 2, still 2 clusters. And save the result here, and we plot it. So this is the result. Okay? And we can also use Euclidean method, Euclidean distance, and see this is a result. Remember, Euclidean or Manhattan, they are just different metrics to measure the distance. But the strategy is still similar. Right? We still try to find the point that is closest to all other points on average. So in this example, no matter which metric we use, we have exactly the same result actually. You see from the index is exactly the same. Right? So for example, we can compare these two results. Right? So calculate PAM-mod 1 clustering not equal to PAM-mod 2 clustering result. but basically comparing their labels, clustering labels, and it's 0. So there's no difference between these two results. Okay. How about K-means and K-Medoids? Is there any difference? So if we calculate, calculate the clustering result of PAM Mark 2 and the clustering result of K-means Mark 2. It turns out that all of them are different. That actually means they just assign the opposite labels. Remember, there is no ground truth in a clustering algorithm. There is no y variable. So the algorithm will just assign 1 and 2 to two clusters. Sometimes they may assign 1 to this one, 2 to this one, or another algorithm may assign 1 to this cluster and 2 to that cluster. But it doesn't matter actually. Turns out that they assign the labels in the opposite way. However, they actually the results are essentially the same. If you take a look at this one and this one, you see exactly the same actually. So this is a PAM method. All right. And then let's take a look at another example. The US arrest data set. So this one contains statistics in arrests per 100,000 residents for assault, murder, rape in each of the 50 US states in 1973. So it's a building data set in R. And take a look at the first few rows, 4 columns, and each observation is corresponding to one state. So totally 50 states. And apparently, the different feature variables have different magnitude. So murder has the smallest magnitude, and assault has the biggest magnitude. So it makes sense to scale the data first. We remove observations with any missing values, and then scale the data. So this is a description of the scale function. So by default, actually, center equals true and scale equals true, which means minus mean divided by standard deviation. So this is actually the default options for these two parameters. But you can choose to center it only or scale it only for other algorithms. But for clustering algorithm, the recommendation is to scale and center the data at the same time. So after we scale the data and remove missing values, we save the result in US arrests 1. See, this is the result. All of them have the same scale now. And then let's figure out the optimal K. So now we have 4-dimensional data. It's not possible to visualize it using all of the features unless we reduce the dimension to 2 first and then visualize the result. So if we don't visualize, we don't do dimension reduction and visualize the result, we don't want to guess, we can again use this function to figure out the optimal K. So now turns out that the optimal K is 2. So this is a very good example that the optimal K may not be the one that is corresponding to the biggest gap statistic, right? So this one, when K equals 4, the gap statistic is the biggest. However, this is not an optimal one. Instead, 2 is the optimal K, right? Because this is the smallest K such that it is greater than gap K plus 1 minus 1 standard deviation. This is the first time. So this one doesn't work. This is smaller than that. This one won't work. But all of these actually also greater than the lower limit of one standard deviation interval. Anyway, K is 2. Now we can apply the K-means function to do a K-means clustering. Specify 2. So this is the result. If we plot using this function. So let's see, where is Pennsylvania? Yeah, the Pennsylvania is here. Only 2 clusters. And if we use the PAM method, still 2 clusters. Same result, exactly the same result. Yeah, Pennsylvania is also here. But, all right. Now we're done with clustering. Not clustering, this is partitioning clustering. Okay, we talked about K-means and K-Medoids. And we also learned how to find the optimal K using a function. And then let's move on to hierarchical clustering. So this is a different approach, very different approach. So first, it does not require to pre-specify the number of clusters to be generated. So you don't have to guess how many clusters. And the result of hierarchical clustering is a tree or a dendrogram. But this tree is sort of different from a decision tree. So remember, this is an unsupervised learning model. A decision tree is a supervised learning model. For a decision tree, the tree grows from the root, from the top, and then gradually grow downward, right? So this is a decision tree. But a dendrogram or hierarchical clustering tree grows from the bottom, from the leaves. So it will start from odd observations on the bottom and try to combine them together. And then gradually combine them together until all of the observations are in one set, which is the root. So, and trees can describe degrees of similarity between different objects, regardless of how those relationships came to be. So it will provide more information than the previous partitioning clustering. It not only provides the labels, clustering labels, it also tells you the relative relationship between all the observations in the data set. And let's see, there are 2 main steps in constructing a clustering tree. So first, represent each case as a point in a Cartesian space. So basically, it will, as I said, it will put all of the observations on a straight line, somehow like this, one-dimensional, right? And the points that are closer to each other will be put together, right? So they are actually somehow ordered, right? It's not a random list of observations. They are the distances have already been calculated. Then make branching decisions based on how close together the points or clouds of points are. So for example, naturally you will connect these 2 together and then these 3 together and then these 3 together. And in terms of distance, these 2 clusters, small clusters are similar, closer. So we'll combine them together to a bigger branch first, and then finally put them all together. So this is how we grow a dendrogram from the bottom to the top. Okay. So let's see one example. We will use the US arrest data to build a tree. So take U as a rest and scale the data first. And then we use, so this one is used to specify the metric that is used to cover the distance. And so DIST stands for distance, and we use Euclidean. And then hierarchical clustering tree, H-clust. So this function is a base R function, I believe. And method equals word D2. So there are some options for this method. So this is, I think this is probably the default option. Right? And then save the result here. And then we can plot the tree. So you can see this nice looking tree. So see all of the 50 states are listed at the bottom on the straight line. And then the tree gradually grow from bottom, starting from combining two states together first. We see Alabama and Louisiana, and then Georgia and Tennessee, and then together, gradually go together. So let's see, where is Pennsylvania? Pennsylvania is here. So in terms of crime data and population data, the closest state is Ohio, which makes sense. Okay, we're kind of similar. And then the other branch is Oklahoma, Indiana, and Kansas. So all of them together. So we are kind of close in terms of crime data and population data. Right? But we are very far away from Alabama in all of these. Right? And additional information is provided by the length of the branch. Right? So for example, so you see, so these two are relatively long, which means these two clusters are kind of far away from each other. And if you take a look at these two, the length of these branches, so they also denote how far away these two branches are from each other. The longer the branch, and the more far away the two clusters or the two observations are. Okay? All right. So this is a clustering dendrogram. Very simple to create it. And of course, one restriction is that for large data sets, it will be very difficult to create a visible dendrogram. Now imagine if you have 1,000 observations, all of these labels will be clustered together. Okay, it's very difficult to tell any observation, the label for any observation. Alternatively, we can use this function to plot the tree. Right? So still, you need to fit the tree using the H-clust function. And then you can choose to use this FV's dent function to plot the tree. Right? If you use this function, you have the option to specify how many clusters you want. And then the algorithm will automatically put a border for each cluster. For example, if we say k equals 2, and then you see it will automatically create separate the two clusters using this borders. Okay, and you can also choose color palettes, and yeah, so this one is used to add rectangular around groups. All right, and you can also, if you think we need 3 clusters, for example, okay, then you can just let k equal 3. Then you see the right cluster is further separated to two smaller clusters. And now we have three clusters. Right. So of course, this K should be decided by some other function or from some expertise, experience, etc. Okay, judgment. Um, but anyway, this is a way to visualize a tree in a better way somehow.